So this is the Redox longer answer questions, and we're just looking at question 2 in this video. So this is what looks like a longer question, 8 marks in total, although it is actually split up. So it's more like really a series of shorter 2 or 3 mark questions to cope with. So we have chlorine gas bubbled through a solution of bromide ions. So that's going to be important, and through a solution of iodide ions, so 2 separate reactions. Organic solvent was added and each mixture was shaken, so that's going to be important for the observations. So in terms of observations, I'm also going to talk about anything that you might not need to know for your exam board. There is one little part. So chlorine gas goes through a solution of bromide ions. So what's happening there is chlorine is displacing bromine, and so we can separately answer the question for chlorine and bromide. And so actually I'm going to write the ionic equation, because writing the ionic equation helps me to see what's formed and therefore identify any colour changes. So chlorine is Cl2, bromide is Br minus, we're displacing to form bromine, the element, and I'm just balancing it as I go along, 2 chloride ions. That's a really important ionic equation to just know, to just really be comfortable with producing displacement reactions. So I've written an ionic equation for that first one, so that's 1 mark already. Colour changes then. Most of us would be happy in talking about the colour of the bromine appearing. So a sort of orange, yellow. It's really quite flexible on the colours of bromine. I would tend to go for orange in aqueous solution, reddy orange if it's made as an element. And so one thing that you want to avoid to just really up your specificity is to talk about a colour change and not just what colour it ends up. So the colour change before I add the organic solvent is from green, because it's chlorine gas, to orange. And I'm going to put the from green in brackets. It's unlikely you would have it. Normally you would just add chlorine solution incidentally, and if you added chlorine solution it wouldn't be green, it would be colourless. So there's my colour change. And then when I add the aqueous solvent, so when you add this in a test tube, you get 2 layers formed. So the aqueous layer goes on the top, on the bottom, so it's more dense, and the organic layer, so when organic we're talking about something like hexane, cyclohexane. You may have used it as something called volatile. Either way, it's a non-polar solvent. So halogens are really soluble in non-polar solvent, which means that the colour, the coloured substance, the halogen, will go into the organic layer. And so the organic layer in this case will turn orange. So most of the bromine will go from the water to the organic layer. I think it's AQA doesn't actually require knowledge of adding organic solvents to halogens, so in that case you would just stick with the ionic equations, the colour changes, and the trend in reactivity that we're going to talk about in a moment. Okay, so let's now do the same thing for chlorine and iodide. So chlorine plus iodide, almost identical ionic equation. Incidentally, it's not asked for state symbols. It would be relatively easy to do state symbols for this. Everything would be aqueous except the initial chlorine gas. But because iodine's not very soluble, etc., we'd probably just not bother with the state symbols. So we're starting with a green gas again, but this time the solution turns brown. Sometimes iodine does look a little bit orange, but you might as well remember it as being brown in aqueous solution so that it's distinct from bromine, otherwise you're just going to confuse and start calling bromine brown. So the solution turns brown. That would be a mark, and we've got my half equation. And then observation for the organic solvent. Again, you should know whether you are meant to know this. I'm relatively sure it's only AQA that doesn't need to know this. The organic solvent, very, very distinct colour change in that it will turn purple when you shake it up with iodine. It's a really easy way. We just said that iodine sometimes looks kind of orange and bromine sometimes looks brown. It really depends on concentration. Organic solvent is a really easy way to tell the difference between bromine and iodine because the colour is very, very different with iodine. And then the last bit, so we've already got probably looking at 2 marks for my ionic equations and then another 2 marks for each of the observations. So we've already got 6 marks. We're not looking for a massive amount of information for my state and explain the trend in reactivity. So don't forget to state the trend, which is that chlorine is more reactive than bromine and iodine, as shown by the displacement reaction. If you really want some brownie points right now, and if you really want to make your wording more specific so that when you start doing more about redox next year, you're ready, then even better than saying chlorine is more reactive would be to say that chlorine is a stronger or better oxidizing agent. That is really good terminology to get to grips with because it's going to make a lot more sense when you start looking at things that are not in the same group reacting in redox reactions. Okay, so chlorine is more reactive than bromine and iodine. Explaining the trend is simply that we've got a smaller atomic radius. So chlorine is more able to attract electrons, or words to that effect. There's a few different ways that we could say that as we're going along. We could say there's less shielding, and so there's much stronger attraction to the outer shell, is more likely to gain electrons. Anything along those lines. If you were writing it absolutely superbly, you could say that it gives out more energy in its electron affinity, but that would only be if you've done Born-Haber cycles, and it's not really necessary. So we're looking at the group trends, the idea that it has a smaller atomic radius, fewer shells, that would work as well, less shielding, stronger attraction to outer electrons, more able to attract electrons, more able to remove electrons from other elements. Something along those lines to explain the trend in reactivity.